Scaling describes how one quantity changes in response to changing another quantity by either multiplication or division. The first type of scaling we'll look at is called linear scaling. Proportionality describes situations where two quantities scale linearly. One way this can happen is with direct proportionality. What this means is when one quantity doubles, the other quantity doubles. An example of this from real life: if the price of gasoline increases by 25%, then the cost of filling your 10-gallon gas tank will also increase by 25%. And of course, if the price of gas doubles, then it'll cost you twice as much to fill the tank. Another type of proportionality is inverse proportionality. When you have inverse proportionality, when one quantity doubles, the other quantity is cut in half. A simple example of this is if you triple the number of friends that you invite over to share your cake at your party, then you'll have to reduce the size of the cake slice for each guest to 1/3 in order for there to be enough cake for everyone. Mathematically, the expression for direct proportionality is y is equal to kx, whereas the expression for inverse proportionality is y is equal to k times 1 over x. The symbol k is just a number, often called the proportionality constant. Another type of scaling that appears commonly in physics classes is quadratic scaling. Quadratic scaling describes a situation where a change in one quantity by a certain factor causes another quantity to be increased by that factor squared. For example, if you were ordering a square dance floor to be installed for a party, if you triple the length of the square-shaped dance floor that you want, you will increase the area of the floor by a factor of 9, because of course 3 squared is equal to 9. The mathematical expression for quadratic scaling is y is equal to kx squared, where again k is that proportionality constant. It's just a number. Why is scaling important? Understanding how variables scale in a physics equation helps us to understand how physical quantities are related to each other, which is an important step in developing an intuition for cause and effect in physical systems. Let's take a physical example. Here's an equation that describes the motion of a hockey puck on a frictionless surface like an ice rink. D stands for the displacement, how far the puck moves. This symbol V0, or V0, is the initial velocity. It's the start speed. How fast is the puck moving to start with? T is just the time. How long do you push the puck for, or how long do you observe the puck being pushed for? F is the amount of force that you apply onto the hockey puck. And m is the mass of the hockey puck itself. If we substitute the symbols in the equation for their meanings, we get something that might be a little easier for a beginning student to understand. Let's consider some special limiting cases of this equation. Let's start by considering a scenario where we don't push the puck at all, but that it does have a starting speed at the beginning of the experiment. The equation then tells us that if we apply no force, then if we wait twice as long, making time our variable, then the puck will move twice as far if we keep the starting speed the same. In this scenario, the starting speed is a constant. That is our proportionality constant, k. And we have an equation that says that the observed quantity is equal to a proportionality constant times the quantity that we change. This is a direct proportionality equation, and so if we wait for twice as long with the same starting speed, then the puck will go twice as far. On the other hand, we could take the same equation and set the time that we observed the puck for to be unchanged. In that case, this becomes our proportionality constant, and our equation becomes how far the puck goes is equal to a proportionality constant times the starting speed. And if we change the starting speed while keeping this proportionality constant of how long the same, then we again have a direct proportionality equation. And so if we double the start speed, we'll double how far it goes. And if we have the start speed, the puck will move half as far in that same amount of time. Let's consider a different limiting case, where the puck starts with zero velocity, that is, it's at rest, but we do push on it. So if we start from rest, then if we push twice as hard, but leave everything else the same, so that how long we observe it for and how long we push it for doesn't change between experiments, and how heavy the puck is doesn't change. The only thing we change is how hard. If these are now constant for our experiment, this becomes our proportionality constant, how long squared over how heavy. Our equation then tells us that we have a linear proportionality between how far the puck will move and how hard we push it, with this being the proportionality constant k. So if we push twice as hard, the puck will go twice as far in the same amount of time, and assuming the puck does not change its weight. Instead, we could change how long we push the puck for. If we don't change the force and we don't change how hard the puck is between different experiments in this scenario, then this ratio becomes our proportionality constant k. And our equation now tells us that we have a quadratic scaling of the observed variable is equal to a proportionality constant times our changing variable squared. And because of that squared factor, if we wait twice as long, the puck will have moved 4 times as far. Finally, we could choose to make the puck twice as heavy, in effect changing how heavy the puck is while leaving the force and how long we apply the force for unchanged, so that this set of terms up top becomes unchanged or constant, and thus our proportionality constant. And we now have an equation that says how far the puck will go is equal to a proportionality constant over the variable that we changed. That's an inverse proportionality, and that tells us if we double the mass of the puck will move only half as far, assuming we've pushed with the same force for the same amount of time.